Thank you. Mastering the DMA and IOMMU APIs. What a pompous title. I mean, it implies that I actually can master it myself to teach you. And a couple of months ago, when I decided to submit a talk proposal for the ELC, I was just started working on an IOMMU driver with the Renesas kernel team. And I thought, well, I'm going to have to learn about IOMMUs, and I'm going to have to learn about how to implement DMA properly. So why not submit a talk about that and just teach people about what I will learn? It turned out to actually be much more complex than I thought. So I'm actually no master today, but I still hope that I can be able to give you a good tour of the APIs and to teach you a couple of tips and tricks. That also means that I can make mistakes. So if you decide to yell at me, throw things at the stage, please favor tomatoes instead of bricks, because bricks hurt. Actually, the DMA mapping API might hurt a bit more than bricks, but that's still to be decided. So the third thing I've learned about DMA is that there's in the kernel one thing called DMA and a totally different thing called DMA as well. Thank you, kernel, for being so confusing. Well, let me elaborate a bit on that. We have on one side what is called the DMA mapping, and on the other side what is called the DMA engine. So, quick question for you. Who's here to learn about DMA engine? Raise your hand. A couple of hands. Who's here to learn about DMA mapping? Raise your hand as well. A couple more hands. Who's here to learn about both? Okay. And who's here to learn about known? What you're doing here? Okay, so good news and bad news. I'm going to talk about DMA mapping. For the DMA engine side, I've actually had a discussion a couple of months ago with a really nice developer who has started working on that and who asked me lots of questions. And he told me that he was going to write documentation about it. I only had to ask him once every day for 2 months. But he told me this morning that I was allowed to give his name, so I'd like the audience to give a big round of applause for Maxime Ripard over there, who's going to provide you with the documentation for DMA engine. Absolutely no pressure at all. Okay, so now we can get started with the real DMA mapping topic. This is really all about memory access. And it's all about memory access when you have several actors in the system, several agents that can access the same piece of memory. So if you get a piece of memory that's only accessed by the CPU, you don't need DMA, you don't need DMA mappings. If you have a piece of memory that's only accessed by a device, if it's specific, if it's private to the device, then you don't need to care about DMA, the DMA mapping API either. But as soon as you have memory that's accessed by multiple agents, then you need to care about that. So if we look at a really simple system, a really simple use case, for those of you who are still in the 20th century with 8-bit microcontrollers only, that's what you would encounter. So you have a CPU core on one side, and let's take a use case where the CPU needs to write to memory, and then you have a device that reads back from the same piece of memory directly. So in that case, what happens is that the CPU will first write to the memory through a memory controller, and then the second step is that the device will just read from the same piece of memory, and everything works, and that's fine. Unfortunately, or fortunately, actually, we're not in 20th century anymore, and we have more than 8-bit microcontrollers today. So the hardware is getting more complex, and we have to deal with that complexity in software. So the first piece of added complexity is what we call a write buffer. And as the name implies, the write buffer is a buffer that is used by CPU to buffer write operations so that the CPU can continue executing instructions while the writes are slowly flushed to memory. And when you have a write buffer, and when your CPU writes to your main memory, well, it first needs, before the device can read data back from memory, it first needs to make sure that the write buffer is flushed to memory and that the data is actually written so that the device can see the same data. Otherwise, you will have data written by the CPU that's still in the buffer but not in the memory, and the device will not be able to see that. Write buffer is still pretty simple. In devices today, we also have cache memory, which is something just a bit more elaborate than write buffer. So it can actually buffer writes and reads. And it doesn't like flush data automatically. So you can have data that's written by the CPU that ends up in the cache that is not flushed to the memory, even if you wait for some time. So you will need to explicitly flush the cache and make sure the data is written to memory exactly like with the write buffer before the device can access that. Just one level of cache, that's pretty old architecture. So nowadays, in most devices, you actually have several levels of cache. So you can have a multi-core system with multiple CPU cores and multiple level of cache memory. So that's pretty much the same way of operation. The CPU will first write data in memory. Then the data will go through the different levels of caches, and the CPU needs to deal with that and to flush the cache before the data can be read back by the device. It has been simplified a bit on some systems with a piece of hardware that's called a cache coherent interconnect. Well, that's one of the names. There are several names for that. But the idea is that it's an interconnection network that makes sure that the device view of the memory will always be coherent with the CPU view of the memory. So when you have coherent views of the same piece of memory, when the device writes to the main memory, the data could end up in the cache and not be written in the memory. But when the device will read back the data, then the device will go through the cache coherent interconnect, and that piece of hardware will go look inside the cache to see if there's no piece of data in there that's more recent than what's available in memory. So it's a simplification, in which case you actually don't need to deal in software with all the complexity, or at least part of the complexity of the caching mechanism. That's all on the CPU side. You can also have caches on the device side, and you can also have MMUs on the device side. So we have MMUs on the CPU side, where you have a virtual view of the system memory for the CPU. But you can also have a virtual view of the system memory for the devices, in which case you actually need to program the IOMMU in order for the device to be able to access the memory at all. So in that case, the CPU will write data to memory and needs to program the IOMMU to ensure that the device can have access to that piece of memory. And then the device can read the data from memory directly. You can have an IOMMU with a cache coherent interconnect or without one. So there's lots of combinations that are possible today. Real systems that we have now are even more complex than that. So you can have lots of CPU cores that can be grouped in clusters with different levels of caches, some local to the CPU, some shared between CPUs in the same cluster. You can have a big reordering matrix in the middle that connects all the pieces together, and that will just reorder writes and reads to memory. So it can really be a complex problem, and you can't really think about a system. You can't have a sequential view of the system. You can't think, my CPU is going to write data in memory somewhere, so that data will be written, and then when I do a second operation, it will come after that. There's no concept of before and after anymore. What we have is concept of who can see what's data in memory and how to synchronize between them. So there's lots of complexity in the hardware that we need to deal with. And that's in ARM hardware, but that can also be in different kind of hardware. So the real core concept that we need to understand to really be able to use DMA and actually access memory correctly is the concept of memory mappings. When you have memory in a system, when you have physical memory in your system, that memory is not owned by anyone. And you can't access the physical memory before you give the rights to either the CPU or to a device or several devices to access that memory. So the act of giving a view of memory and giving the right to access the memory for an agent in the system, that's called mapping the memory for that agent. And we have several kind of mappings. The easiest one is what we call a fully coherent mapping. That means that all the agents in the system, when they write to memory, that write will immediately be visible to all the other agents in the system. So you write to memory somewhere, everybody else in the system can see the write immediately. So you don't have to care yourself in the CPU about the caches, for instance, because the view is totally coherent. There's several ways to achieve that. One way that I mentioned is to use a cache coherent interconnect in the hardware that will do the job with you. A different way is to just disable the cache. If you disable the cache for a piece of memory, then, well, the mapping is fully coherent. It's not that you can't think about memory being cached or uncached. Caching is not a property of the physical memory itself. It's a property of how an agent, a device, or a CPU sees the memory and accesses the memory. So when you map the memory to the CPU, telling this physical page can be accessed at this virtual address, then you also give attributes saying, I want that access to be cached or to be uncached. So really, caching is a property of the mapping and not of the memory itself. Then we have what we call the write combining mappings. That's mostly like fully coherent mappings, except that the writes can be buffered. So when the CPU writes lots of data to a buffer, they can be to memory, they can be put in a buffer and then written like in bursts, in fast access. But you can really have buffering in the system. That's mostly used for graphics, where you want to just draw a frame in a piece of memory, then render that with the hardware. And basically, that's usually, especially on an ARM system, uncached memory, but with a bit of set in the mapping that says we can combine the writes. Then we have a weird beast that's called a weakly ordered mapping. That means that when you write and read to memory, you do that sequentially in the CPU, while the reads and writes can be freely reordered by the system. And that involves adding explicit support for sync points and barriers in the system when you say, okay, I've written data to memory, then I want to make sure that it goes to memory before I do anything else. Systems that support weakly ordered mapping that's not cached are really uncommon. Usually that's what you use for system memory that's cached and with a weak ordering. And then we have the completely non-coherent mappings. And those are just mapping that can be cached, where there's absolutely no guarantee on the order of operations, when a single write from the CPU could actually end up in multiple writes in memory, or could be grouped. So there's really no guarantee in that. And when using that kind of mapping, you need to guarantee in software that you will actually handle the synchronization of every component in the system. Yep?
In the previous slide, where you showed the diagram,
usually the write buffer is close to the CPU core. You can still have a write buffer when you have an uncached mapping, yes. It really depends on the implementation, but usually the write buffer is a separate piece of hardware than the cache. So, no, it's not inside a cache. Well, I guess it could be, depending on the implementation. It really depends on the architecture. So the explanation here is pretty generic. It covers different architectures without going into specifics. But yeah, then it really depends. So we have different kind of memory mappings, and we know that we need to handle the cache for at least some of them. So we have APIs in the Linux kernel. There's a header that includes APIs for cache management, and especially for flushing the cache and making sure that data ends up in memory. Not everything exposed by that API. There's especially no explicit support for different levels of caches. And there's also, the API is targeted at flushing the cache from a CPU point of view and user space mappings, the kernel mappings, and it doesn't take devices into account. So we have another header that's called autocache, where you have functions that deal with the second level of cache. And there's one really important rule about that API is that you must not use it in your drivers. So if your driver is including those headers, it's really good sign that you're using something wrong. And the reason is that the autocache API, that's totally architecture specific. So if you're using it, then your driver will not be portable across architectures. Even the cache flush API, that's more or less generic, but it's targeted for a real, well, not a single purpose, but a couple of real specific purposes. which is syncing the memory when you will map and unmap memory for the CPU and modifying the configuration of the EMMU. So those APIs are not suitable when you want to use DMA. Don't use them. So now that we know what we should not use, maybe we should talk about what we can actually use. So for that, we have what is called in kernel a DMA mapping API. And that API, well, there's several purposes to it. One of them is to allocate memory that is suitable for DMA operations. So not all memory in the system is suitable to be accessed by both the CPU and devices. So we need to make sure that we will actually allocate memory that we can use for that purpose. That's one of them. The other one is to map that memory to user space processes, because you might need a buffer to be accessible from user space, and to also map it to devices, because you might have several devices that need to access that memory. So it's really mapping and unmapping that memory and giving access to that memory to different agents in the system. And one last purpose of the API is to be able to synchronize access to the memory. So when you've accessed memory from the CPU, you've written to the memory by the CPU, and now you know you don't. You need the data to be accessible by the device. Then you have an API that you can use to say, okay, I'm done. Give ownership of the memory to the device, because the device will need to access that. The DMA mapping lives in the header that you can actually include in your drivers. Everything is accessible from there, but inside that, there's a couple of other interesting headers. I will not go into too much details, but we have, there's one that defines all the attributes that come with DMA mappings, one that defines the different directions, so DMA from the device to memory, from memory to the device, or both. And there's also an interesting header called DMA mapping broken. That means that if your platform doesn't have support for DMA, that header will make sure that your driver still compiles, but it will not link. So it will not crash everything at compilation time, but it will not link. So we'll definitely see that there's a problem. So if you need DMA support in a driver, if you need that API, you need to make sure that your driver depends on config has DMA. Otherwise, it will not work. Then there's an architecture-specific part of the implementation that can actually include a couple of headers that have helper functions for generic parts. It's a bit confusing, actually. That's one of the problems with the DMA API, mapping API implementation. It grew over time, and it got a bit confusing and complex, and that's something we should fix at some point, but we'll get to that later. Let's start with DMA coherent mappings and how to create them and manage them. So a DMA coherent mapping is created with a function that's called DMA alloc coherent. And you can then describe that with DMA free coherent. So that function will really allocate memory that's suitable for DMA. It will return a pointer to the virtual CPU address for the kernel, so that the kernel driver can access that memory. And it will also return in the DMA handle argument an address, a device address that the device can use to access the memory. That's not a physical memory address. When using the DMA mapping API, you don't touch physical memory addresses. In many cases, that's actually correspond to physical memory. But when you have an IOMMU that remaps addresses between the device and physical memory, then they're not identical. So you must not think that the DMA handle is a physical address, and you must not try to use function that implies that you will have a physical address. So it's really a view of the memory from the CPU side. That's the pointer that is returned by the function, and a view of the memory from the device side. That's the DMA handle, but there's no access to the physical memory underneath. DMA free coherent will just free that block of memory, so you give it the exact arguments that you gave to the allocation function. So that's pretty simple. That function can be pretty expensive. So creating a coherent mapping, well, first of all, usually that will allocate memory in page-sized chunks. So if you need lots of small buffers for DMA, we have an API for that. That's the DMA pool API that will allocate pages and then split them in small pieces. So that's something you can use. But you need to be aware that this can allocate quite a lot of memory. So that's suitable for big buffers, but for really small buffers, that's not the right API. There's a different API that's been introduced later that's called the DMA alloc attributes and DMA free attributes. That basically is more or less the same than DMA alloc coherent and DMA free coherent, except that you can pass an optional pointer to attributes that you can use to control, well, to have a fine-grained control on the allocation process. If you pass a null attributes, it will have exactly the same behavior as the previous functions. So what kind of attributes do we have? We can tell the allocator to allocate memory that has a right combining mapping for the CPU. We've seen what that means before, so that's a way to allocate that kind of memory. There's also an attribute that you can use to allocate weak ordered mappings, and that's actually implemented by the cell platform only and not used by any driver. So I'm not sure of the usefulness of that. There's also an attribute that you can use to allocate non-consistent mappings, and that's, well, not all of those attributes are implemented in all architectures. So that can be a bit tricky, and that can be considered as a bug, obviously. If you need a feature and it's not implemented by the architecture there, well, please go ahead and implement that. But non-coherent mappings, non-consistent mappings, then not implemented in ARM, for instance. It's also, just a side note, consistent and coherent are two words that mean the same in this context. So I can use one or the other freely, and the API actually uses both. That can be a bit confusing as well, but they really mean the same. I'll skip the right barrier, that's there, but it's really weird use cases. False contiguous is a pretty interesting attribute. When you allocate memory and you want it to be accessible by a device that has an IOMMU, there's no need to allocate physically contiguous memory. But you can use that attribute to force that allocation, which can lead to more efficient results because the IOMMU will have an easier job. Then another attribute that's pretty interesting as well is that you can completely skip the kernel mapping. You can allocate a memory buffer, and if you know that you won't need to touch the memory from the CPU inside the kernel, then you don't need a pointer to that memory, you don't need a mapping for that memory, because creating that mapping can be expensive as well. So you can tell the system, I need a buffer that I will need to share between devices. I will need one device to write to that buffer and different device to read from the buffer, but I don't need to touch the memory from the CPU. So please allocate a buffer without mapping it to the CPU. And then there's the last one that you can use to actually skip cache operations. You need to use that with care, because when you need to handle the cache, then you should definitely not skip that, but we'll see later how it can be used. No, it returns a cookie that you must not difference. So use that cookie for the other functions in the API, but you definitely must not difference that cookie, otherwise, well, the system will crash. So it's pretty easy to find. Yep? So no kernel mapping means the CPU doesn't need to touch the memory itself, so don't create a mapping. And the other one is there's a kernel mapping, there's a CPU kernel mapping, but we want to skip cache handling, for instance, because the memory is fully coherent, so we don't need to handle the cache in that case. Or there can be a couple of other use cases that we'll see. Yes. So I'm talking about alloc coherent, but if you look at the previous slide, so it's a bit more generic function called DMA alloc attributes. So it takes different attributes. For the allocation itself, it's only the top attribute, and the last one is called for, is used for the map function. So when you have allocated a buffer with non-consistent, for instance, so it's a non-coherent buffer, then you can use the skip CPU thing. And actually, if you look at the implementation, there's a couple of, well, I would call that bugs that will actually try to flush the CPU cache even for coherent mapping. So that can be useful to work around that as well. But yeah, we'll see about it. Now that we have allocated memory, it's pretty important to know that not all of the system memory can be used for DMA. So when we have, for instance, a 64-bit system, or even a 32-bit system with a large physical address extension, you can have physical addresses that span more than 32 bits. But you could have devices inside a system that can only DMA in the low 32 bits of the address space. And so the way to deal with that is that we tell the DMA mapping subsystem that the device has restrictions, and we check that the device capabilities for DMA actually match what the system can provide. So we have two main functions for that. The first one is called DMA set mask, and that will set the device DMA mask for non-coherent mappings. And that's basically a bit mask of all the bits, of all the address bits that the device can touch when doing DMA. So if you have a device that can do DMA in the first 4 gigabytes of the address space, well, that's a 32-bit mask. If you can do more or less than that, then you just adjust the mask. You also have a function that's called DMA set coherent mask, and that one is used to set the mask for the DMA coherent operations. There's a bit of historical reasons why, yep.
What happens if you have a base address?
That's a problem. We don't currently support that correctly. Yeah, well, you shouldn't have that, but that's something that's currently not supported, at least correctly. So you're talking about PCI on the Renaissance platform, for instance. And generically. Exactly. Yeah, so that's a shortcoming of the API, actually. There's also a third function that you can use to set both masks when they are the same for your device, and that's really most of the cases. It's really not typical to have two different masks, so we won't go in details regarding when it can be useful, but really most devices will have the same mask for the coherent and non-coherent DMA. It's a bit tricky also because those functions set the mask inside struct device, and if you look at struct device, there's the DMA mask and the coherent DMA mask, and one of them is actually a pointer, the other one being the value directly. That's for historical reasons mainly. And that means that you first have to initialize the DMA mask pointer to point to a 64-bit integer before you can use the previous functions, which, yeah, it's just painful, but that's the way it is today. And it would be nice to change that in the kernel, but it's used so widely that it's not easy work. So there's one last function that can be used when you have the same mask for both, and that function will actually set the DMA mask pointer to point to the coherent DMA mask member of struct device and initialize that. So that's usually when you have the same mask for both. That's what you should do usually. Now that we've allocated memory, mapped it to the kernel optionally, and seen how to restrict the address space, then we need also sometimes to map the memory to user space. And that's pretty simple. We have API functions for that. So we have a DMA AMMAP attributes function. It takes the same kind of arguments, well, the same arguments that have been returned by the allocoherent function, optional attributes as well, and that maps the memory to user space. There are two wrappers, DMA AMMAP coherent, DMA AMMAP write combined. I just call that function with the right attribute set. So that's a pretty easy piece of API. Now we're coming to the second way to do DMA. So instead of allocating coherent buffers, you can actually allocate memory with functions like getFreePages or kmalloc that will guarantee to return physically contiguous memory. And you can then map the memory to the device yourself. So you don't allocate it with the DMA mapping API, and you just tell the system, here's a piece of memory, I want to map it to this device because the device will need to access the memory. And you need to tell the system whether the device will read and write the memory, whether it will just read, just write it, or doing nothing at all. And if it does nothing at all, I suppose that you actually don't need a DMA mapping API for that. So I'm not sure what the purpose of that really is. You can map a single range of physically contiguous memory. So you give it the CPU virtual pointer, the size, direction, and you can map and unmap memory to device. That will handle all the process of configuring the IOMMU for the device, for instance. So you map and unmap that. And there are two wrappers that just call the functions without any attributes, so that's not that difficult. Underneath, the system will go through all the physical pages of your buffer and map them and unmap them one at a time. And you can do that actually yourself with an API that can be used to map or unmap a page. There's a third way to do the mapping. It's actually, instead of mapping a physically contiguous range of memory, you give the API a scatter list. So that's just a list of physically contiguous chunks, and you ask the system to map that to a device. This will only work when you have physically non-contiguous memory if your device has an IOMMU. Otherwise, if the memory is not physically contiguous, the system cannot give you a physically contiguous view of the memory for the device. So you definitely need an IOMMU to use that. Once you've done your mapping, you need to check the return value. So when you map with those functions, DMA map page and DMA map single, it returns a DMA address for your device. And to check for errors, you must not check the return value directly, because what constitutes an error is really architecture dependent. So there's a function that you can use, you pass it a return value, and it tells you if it's succeeded or if it failed. It's very important to use that, because if you don't, well, the driver will probably work on a platform that you tested on, because you correctly check the return value for that architecture, but when you start using it on a different architecture, it will stop working all of a sudden. Once you've mapped memory to a device, well, the usual way to proceed is that you get a piece of memory that's allocated, you write to that from the CPU, then you map it to the device, you tell the device to read that memory or write to that memory, and then when you're done, you unmap the memory. So that's really a one-off operation. You just go and have a single device access, map the memory, access it from the device, and map the memory, and that's it. When you have a buffer that needs to be accessed once only by device, that's the way to go. But mapping and unmapping can be expensive. I mentioned that it creates mappings for the IOMMU, for instance, and that's an expensive operation. So if you know that you're going to touch a memory from the CPU, then from the device, then again from the CPU, then for the device, and do that multiple times, you should keep the mapping around. But you need to tell the system, when you're done accessing the memory from the CPU or from the device, that the other agent can actually access the memory. So we have synchronization functions. You can sync single, you can sync a page, sync scatter list, exactly like we did for the mapping. And those functions will tell the first function, DMA sync for CPU, will tell, now I know that the device is done accessing the memory. It will not access the memory anymore. I want to access it from the CPU. So it gives ownership of the memory to the CPU, and then you're free to access it on the CPU side. Then when you're done accessing the memory on the CPU and you want the content of the memory to be accessible by the device, you call the other function, DMA sync for device, that will give back ownership of the memory to the device. So it's really keeping the mapping around, but giving ownership of the memory to one component in the system. And you need to ensure in your code that only the component that has ownership of the memory will ever access that. Otherwise, you will have caching issues, and the system will not function properly. You can sync a range, so that's just a piece of a buffer. So you've allocated a buffer, you've mapped it, but you know that you've only written to a small piece of the buffer. You don't want to sync everything. So you can restrict that or sync a scatter list for the device, for the CPU. So it's really the DMA coherent approach, where you locate a buffer in the beginning of, usually when your driver is initialized, keep that buffer, you know it's coherent, you can access it from the CPU and from the device freely without any kind of synchronization. That's the first way. And the second way, DMA streaming, the DMA streaming mappings, then you map and unmap your buffers to the device, or if you want to keep the mappings around for a longer time, then you have to synchronize them. So it's really two ways to deal with that.
Actually, the first way also needs synchronization sometimes.
It depends, yes.
You might need like to put a barrier after you realize before you initiate it.
Yeah, so when we mentioned write buffers, And the way to actually flush the write buffer is the correct way with the kernel API is to put a memory barrier. That's usually a synchronization primitive to make sure that other agents in the system will see the value that you write to memory. And that can be used to flush the write buffers. But that's just for the write buffers, and it doesn't handle caching. So the sync functions, those handle the cache. They can handle other things like when you have bounce buffers or, well, the couple of advanced topics I wasn't thinking about talking about, but we can later if we have time. So they really handle synchronization when you're using the streaming API, but when you have allocated your buffer with DMA or Coherent, then in that case, you might need a barrier to make sure the write buffer is flushed, but you don't need the sync functions because you don't need to actually synchronize the cache and flush the cache. You can do it, but it's going to be expensive and it will not give you anything, so it's just a performance issue. Contiguous memory allocation. We have a physically contiguous memory allocator inside the kernel. It's located inside the Linux DMA contiguous header. The second line should read DMA contiguous.c instead. That's the implementation. And from a driver point of view, from a device driver point of view, it's pretty easy to use. All you need to do, if you use the DMA alloc coherent function, if you want to have physically contiguous memory, all you need to do is just sit back and relax. There's nothing to do. It's absolutely transparent for you. So that's really, really easy. You have a guarantee that the memory will be physically contiguous. From a system point of view, it's just a bit more tricky because allocating physically contiguous memory means that you need to have physically contiguous memory reserved for that. The way it was done before is that we were just carving out a big chunk of memory from the system memory and reserving that for physically contiguous allocation, so that memory was completely lost when we didn't need it for physically contiguous allocation, so that was a big waste of memory. With CMA, the way it works is that it reserves the memory when the kernel is initialized, but then gives it back to the memory allocator in the kernel and telling the allocator, you can use those pages of memory, but not for everything. You can only use them if you can guarantee that when I will ask you to give me the memory back, you can do it. So it can't be used for different types of allocation, like atomic allocation, for instance, things like that. But for most generic allocation purpose, then that memory is usable by the system. And when you will need physically contiguous memory in your device, then that memory will be reclaimed. What was inside of memory will either be transferred to other pieces of memory or just paged out to a swap file, for instance. And then you will have that physically contiguous memory without wasting it. And we have two functions in the implementation. The first one has to be called in the architecture code right after initializing the early memory allocator. And that will just tell the system, please reserve a big chunk of memory for physical allocation. You give it an address limit, so it will not reserve a chunk that's above that limit. And the size of the chunk that's reserved is actually given in the kernel configuration and can be overridden on the kernel command line. And the second function declares, also reserves a piece of memory for physically contiguous allocation, but reserves that for a given device. So you can say, with the first function, it's a generic reservation. You can just say, I want to reserve memory that can be used by any device that needs physically contiguous memory. But you can also, when you have specific needs, reserve that memory for a specific device as well. So you can only reserve one chunk with the first function, but with the second one, you can reserve one chunk per device. IOMMU integration. I mentioned that the DMA mapping functions handle that for you. So when you map a buffer to a device, it will program the IOMMU of that device so that the device can access the buffer correctly. And that's transparent. So we have, well, or at least it should be transparent. We have an IOMMU API in linux/iommu.h that you can use directly in a driver when you want to deal directly with the IOMMU. But in that case, that will not be handled by the DMA mapping API, and you will have to do all the work yourself. And we don't want to modify all device drivers to handle IOMMUs manually, because your device driver in one SoC could be connected to an IOMMU, in another one could have no IOMMU, so we don't want to have explicit support in all the device drivers for that. So the DMA mapping API has support for that. On x86 it does, on ARM it does as well. But on ARM, you still need to attach a device with a specific IOMMU. So we have a couple of API functions, two that you need to call to actually create the mapping between the device and the IOMMU, and the other one to tear it down. And those functions nowadays are called mostly in the device drivers. So it's not totally transparent. IOMMU handling, like the mapping of the buffers, is done by the DMA mapping API, but the initialization is done by the device drivers. And that's not an ideal situation, because we still need to modify all the device drivers when they need to support an IOMMU. So those calls need to move inside the IOMMU drivers. If you're writing a new IOMMU driver, or if you're writing a new driver for a platform, for a device on a platform that uses an IOMMU, please try to move those calls inside the IOMMU driver instead of doing it explicitly in the device. Because when you do so, that means that your device will not have to care about the IOMMU at all, and it will be completely transparent for it, making the device driver much easier. It can actually cause a couple of issues. Because when it's completely transparent, we can still have devices that have special needs regarding the IOMMU. For instance, you could have a device where you want to map a buffer at a given fixed address, because the device expects that. You can have in the device several agents, several bus masters that are connected to different IOMMUs. So those are things that are not currently correctly supported in the DMA mapping API, so it's a couple of shortcomings that we need to work on. Please feel free to help as well if you have that kind of need. It's pretty uncommon, but that's something that can be seen. There's also the problem of power management with the IOMMU. You want to have your IOMMU powered off when your device doesn't use it, and that's something we don't handle correctly at the moment, so that's also something that needs work. On the topic of device tree bindings, well, there's not that much to talk about actually. There have been a proposal, a couple of them, because we've been to version 7, for contiguous memory, for the contiguous memory allocator, and to give device tree bindings, but it hasn't made it to mainline. So I'm not sure what the current status is. I've tried to ping the maintainer and the author of the patch, but I haven't received a reply yet. So that's still up in the air. At some point we'll need it, because I mentioned that the size of the memory that is reserved is specified in the kernel configuration, can be avoided on the kernel command line, but we need to put that in the device tree as well, and we need to have per device reservation in the device tree as well. IOMMU bindings, we have a couple of IOMMUs that have DT bindings, but there's nothing that's common, and more importantly, there's no common binding that can be used to specify the mapping between one device and the IOMMU it uses. So that's something that I plan to start working on shortly. I need it. It shouldn't be that difficult, but at the moment there's no standard DT bindings for that. Now, a couple of, well, tips and tricks and hopefully hints and things that you can find helpful. Well, I've already mentioned that you need to use the right API, so don't use the cache API directly. That will make your driver non-portable. It will make your driver fail as soon as you need to use it on a different platform. Even worse than that, the cache APIs serve specific purposes, and the implementation could be modified as long as it still fits those purposes. If you use them for something else, if you use them for DMA, then there's no guarantee that the same API on the same platform will keep working. So do not do that. Choose between coherent and streaming mapping wisely. A coherent mapping on ARM isn't cached. That means that if you map it to user space and user space needs to read the same pieces of memory repeatedly, then that will be slow. A streaming mapping will be faster for that. On the other hand, with a streaming mapping, which is cached on ARM, you need to deal with the cache and sync the buffers. And that can also be a costly operation. So you need to choose between the two, depending on your use case. Ultimately, that use case should be decided by user space, because it's user space that knows how the buffer will be used, at least in some cases, whether it will just read the buffer, the memory in a single go, or it will need to access the same pieces of memory several times. And we don't have an API at the moment for that, so that's something that we'll need to work on as well. Set the mask correctly, otherwise there will be failure. I mean, it could work in the default case with default masks, but you could have weird issues either at runtime or later when the kernel API evolves. Use the DMA mapping error function to check for error codes, otherwise you will also have portability issues. For coherent mappings, don't call the DMA sync API. I've seen a couple of drivers, and actually even one driver I've written some time ago, so I can be blamed for that as well, that just allocate coherent memory and then sync the cache. That's pointless. It will take time and it's not needed. Try to skip and not to have a kernel mapping if you don't need it, because you also might need to flush the cache for that, and if you don't need to access it, don't create a mapping. Try to also skip synchronization when you create a mapping. So when you need to share a buffer between different devices, you need to map it to all the devices. Mapping a buffer will sync the CPU cache. If you map it to two devices, the first map operation will sync the CPU cache, the second map operation will sync the CPU cache as well. And that's pointless because it just has been done. So you can use the skip CPU sync flag attribute to be able to skip that when you map your buffer to several devices. I think I'm done for the tips. Now we have a couple of problems and issues that I actually already mentioned before. It's really that the DMA mapping API evolved over time. So there are things that are not clear or clean, like the way the headers are structured. That should definitely be refactored. Like the DMA set mask and set coherent mask API. So works need to be done there. We also have issue with the sync functions. Those functions, well, sync the cache, but they don't take attributes at the moment. So that means that you can't give them an attribute to skip syncing the cache. You might say that a function whose purpose is to sync the cache should not be called in the first place if you don't need that. But those functions might actually do a bit more work. They don't on ARM at the moment, that might in the future. So when using the DMA streaming mapping, it would be nice to have attributes for those functions when you know you can skip the cache sync, but you might not want to skip the other operations. There's also a couple of more advanced topics that I can talk after if well, time permits, not really. But if anyone is interested, like the DMA pool allocation, the generic coherent allocator inside the kernel that can be used by architecture to implement the DMA alloc coherent API. There's also a DMA alloc non-coherent function and a DMA cache sync function that goes with that. It isn't used much, and it's an API that hasn't evolved much over time, so that's something that needs to be cleaned up and that needs to be integrated better with the rest of the API. So it's really something that evolved, and you will find things that will be confusing, and you will ask yourself, why is it done that way? And mostly, in many cases, for historical reasons. So I plan to work on that. A couple of resources. There's documentation in the kernel, which is actually quite good. So I wanted to mention that. There's really nice set of article about memory access ordering and memory barriers and cache management on that. So it's something that really I really advise you to read. It's not mandatory. It's not only for DMA, but it's really, really interesting. And there's also one article about, well, I actually have forgotten what it's about, but I'm sure it's really interesting as well. Well, two main mailing lists if you need contact and my email address, but as I mentioned in the beginning, I might not be the best person to answer questions, so feel free to send me a mail, but copying the Linux ARM kernel or Linux kernel mailing list is definitely a good idea. Questions? Yep.
So I've been confused about why the DMA palette non-coherent is not implemented on the ARM.
That's a good question. Yeah, sorry. So the question is that DMA coherent is not implemented in ARM and you find that confusing. Non-coherent, sorry. Yeah. So it's not implemented in ARM or ARM64, and I actually find it confusing as well. And to be honest, I'm not sure why. So I think we should give it a try because it's definitely a useful API if you want to allocate a buffer that's physically contiguous because your device needs it. And you want to go through CMA, for instance, for memory allocation, but you don't need a coherent mapping in that case. I think that's a good API. What drivers do today is that they allocate the memory using get-free pages or kmalloc when you need smaller sizes. So that gives you physically contiguous memory, but CMA is not used in that case, so that can be a problem for big buffers. And that's how they can allocate memory for non-coherent mappings. But DMA lock non-coherent is something that I think we should implement on ARM. There are many platforms on which it's implemented and where the mapping is actually coherent because those platforms are fully coherent, like 686, for instance. There's no difference between a coherent and a non-coherent mapping. So DMA lock non-coherent on that platform is really an alias for DMA lock coherent. But on ARM, that's not the case, and an implementation would be nice, yes. There's just one platform, I think it's OpenRISC, that has a DMA alloc non-coherent implementation that actually allocates non-coherent memory. But that's the only one I know about. Other questions? Lunchtime? Well, thank you.